Every model so far measured distance, margins, or splits. This one just asks, how likely is this, given everything I've seen before? That's it. That's the entire idea behind naive Bayes. It's quietly running behind more spam filters than almost any other algorithm. And it's built on one assumption that's technically wrong and works anyway. This is episode 12. Naive Bayes explained the math behind spam filters. By the end, you'll build a spam filter from probability alone. Everything here builds on one 250-year-old formula, Bayes' theorem. It answers one question. Given this evidence, how likely is each outcome? P of A given B equals P of B given A times P of A divided by P of B. That's it. That single formula is the entire engine behind this model. Three terms are doing all the work in that formula. The prior, how likely is spam, before you've even read the message. The likelihood, given spam, how likely are these exact words? The posterior, your updated belief after actually seeing the evidence. Naive Bayes just picks whichever posterior comes out highest. Here's where the naive in naive Bayes comes from. It assumes every word is independent of every other word, given the class. That's obviously false. Words absolutely depend on each other in real language. And yet, treating them as independent still produces genuinely useful predictions. A wrong assumption that happens to be a very useful shortcut. So how does this actually turn into a spam filter? Every message becomes a bag of words, just word counts, order thrown away. For each class, naive Bayes learns how often every word tends to appear. A new message shows up, count its words, and multiply their probabilities together. Whichever class comes out more probable wins the vote. There's a practical problem with multiplying lots of small probabilities. Multiply enough numbers under 1, and the result underflows towards 0. The fix: take the log of every probability and add instead of multiply. Same ranking, same winner, just numerically stable under the hood. One more problem. What if a word never appeared in training at all? This probability is 0, and multiplying by 0 wipes out the entire prediction. Laplace smoothing fixes this. Add a small count to every word, even unseen ones. That's the alpha parameter, how much fake evidence you hand every word. Too little smoothing breaks on rare words. Too much and it drowns out real signal. Naive Bayes actually comes in a few different flavors. MultinomialNB, word counts, the default choice for text. BernoulliNB, just whether a word appeared at all, ignoring how many times. GaussianNB, continuous features, assumed to follow a normal distribution. Same core idea, three different assumptions about what your features look like. In scikit-learn, this is MultinomialNB. Vectorize your text with count vectorizer first. Words in, numbers out. Then it's the same pattern as every model this series. .fit, .predict. The alpha parameter controls smoothing one keyword, same as always. Real demo, 30 spam messages, 30 ham messages, bag of words vectorized. MultinomialNB with default smoothing, 100% test accuracy. The words it leaned on hardest: free, click, prize, discount, pure spam signal. Now push alpha, the smoothing strength, up to 2 or 5 instead of 1. Accuracy drops to 94.4%. Too much smoothing blurred the signal. One parameter and a perfect classifier started missing spam. Naive Bayes shines on text, spam filters, sentiment, topic tagging. It's fast to train, fast to predict, and works well even with limited data. The independence assumption hurts more when features are genuinely correlated. It's also a great baseline, quick to try before reaching for anything heavier. For text classification specifically, it's still a serious contender. Let's lock in what we covered. Bayes' theorem, updating belief from prior to posterior using evidence. The naive assumption, treating features as independent, even when they're not. Bag of words, turning text into countable evidence per class. The log trick, adding instead of multiplying to avoid underflow. Laplace smoothing, the alpha parameter that keeps zero frequency words from breaking things. If Bayes' theorem just clicked for you, subscribe, Ensemble Learning is next. Quick look at where we are in the series. We've now covered SVM, KNN, and the probability-driven world of naive Bayes. Episode 13 moves into ensemble learning, combining multiple models into one. Bagging, boosting, and stacking 3 different ways to team models up. Episode 13, Ensemble Learning Explained. Why a team of mediocre models can outperform one great one. Bagging, boosting, and stacking all in one episode. Subscribe to catch it. Your challenge task for this episode. Build a small labeled dataset of spam and ham text messages. Task 1. Vectorize it with Count Vectorizer and fit MultinomialNB. Task 2. Check test accuracy on messages the model has never seen. Bonus. Sweep the alpha parameter. Does smoothing actually change your result? Try it yourself first. The full solution is in the repo. Post your accuracy and whether smoothing helped or hurt in the comments. One wrong assumption. A formula from 1763. A working spam filter. That's naive Bayes, simple math, surprisingly hard to beat. Episode 13, Ensemble Learning Explained, drops next. Subscribe. Comment with your own spam filter accuracy. I'm Majas. This is CodeToAGI. Let's build.